Welcome to example number 1. This is a question about an electron that is moving within a uniform electric field. This uniform electric field is created by using two large conducting plates that have charges that have equal magnitude and opposite sign. The strength of this uniform electric field is given as 2.8 to the power of 3 newtons per coulomb, and the distance between the two plates is 6.36 millimeters. In part A, we're asked to determine the amount of work that would be done in moving the electron from one side to the other side of the plates. In part B, we're asked to determine what would be the speed as the electron strikes the upper plate. So the first thing we would do in a problem like this would be to draw a sketch of this scenario, which has already been shown for you. You can see that the electric field lines have been drawn directly downwards and they are parallel and equally spaced, and they always go from the positive plate to the negative plate. Since the electric field is constant in magnitude and direction, that means the electric force acting on the electron will also be constant in magnitude and direction. So let's calculate the amount of work that is done in moving the charge from the negative plate to the positive plate. We're going to use the definition for work that we used back in the mechanics section. If you recall, work is equal to force times displacement times the cosine of the angle between the force and the displacement. In this particular case, the force acting on the charge is the electric force, the distance that it moves is d, and the angle between the displacement, which is up, and the force, which is up, is 0 degrees. And the cosine of 0 degrees is 1. And the magnitude of the electric force is equal to the charge times the strength of the electric field. Since we're just looking for the magnitude, we're just going to put in an E instead of a negative E, and then multiply by capital E, which represents the electric field strength. So the work can be calculated by multiplying the charge of the electron, or the magnitude of that, multiplied by the electric field strength, then multiplied by the distance that it moved, d. Now let's substitute the values. The charge of an electron, or the magnitude of that charge, is 1.6 to the power of negative 19 coulombs times the electric field strength, which is 2.80 times 10 to the power of 3 newtons per coulomb, and then the distance that is moved in meters is 6.36 times 10 to the power of negative 3 meters. And this gives you an answer of 2.85 times 10 to the power of negative 18 Newton meters. If you look at it, the coulombs will cancel out here, and a Newton meter is the same thing as a joule. Okay, let's move on to part B now. Let's determine the velocity of the electron as it completes this distance of 6.36 millimeters. Okay, so we have one important assumption. We'll assume that the change in kinetic energy is equivalent to the change in electric potential energy, because we're going to assume that the loss of electric potential energy will be entirely converted into an increase in kinetic energy. Now, the loss of electric potential energy can be calculated in several ways, but since we've already calculated the work done, and you remember the work energy theorem, the amount of work done should be equal to the electric potential energy that is lost. So the electric potential energy lost is equal to 2.85 times 10 to the power of negative 18 joules. So now we have the kinetic energy formula is 1/2 mv squared. We're going to assume that the initial velocity of the electron is 0. So the final velocity, okay, squared times the mass times 1/2, will be equal to the work done, which is 2.85 times 10 to the power of negative 18 joules. So rearranging for the velocity we have the following expression, and then now we're going to substitute in, and you'll notice that I've got the mass of an electron here, which is 9.11 to the power of negative 31 kilograms. And then when you plug that all into your calculator, you'll get 2.50 times 10 to the power of 6 meters per second. So a couple things just to reflect about this. You may notice that the work is directly proportional to the force and the displacement. Of course, the force is in proportion to the electric field strength. So if you increase the electric field strength, you increase the work done. Or if you increase the distance that the electron moves, of course, you'll get more work done as well. And the more work being done, then the higher velocity that the electron will attain. Now you could solve part B using a completely different method. You could figure out, for example, the acceleration by using the force divided by the mass, and then you could find the velocity by using v squared equals the initial speed squared plus 2 times the acceleration times the displacement, which is d in this case. That's just an alternative way to doing it, but it's nice to see it at least. You might also note that had this been a positive charge like a proton, the charge would have to move in the opposite direction for the work being done, and you would get the same amount of work because it would be still the same amount of charge and electric field and distance. However, the velocity of the proton would be different because it would have a different mass. Okay, and that's it for example number 1.